Okay, so we've looked at left and right point methods. Now we're going to look at midpoint, meaning the point between left and right point. And I'm going to kind of bounce back and forth between the three lessons that we've done, so the two lessons we've done so far, which is left and right. All right, so here's our left point method. And we're going to be doing the same graph, 1 minus x squared. With the left point method, we used all the points on the left and we ignored the right point. With the right point method, we basically ignored this first left point, used all the points on the right to determine the height of our rectangles, and we used the rightmost point. You can now see that for the midpoint method, we're going to start with the middle point, the point between all of these different x values. So we're going to start with negative 1.5, which is between negative 2 and negative 1.5. That will determine the height of our first rectangle. So we were plugging in negative 1.75 into our function to determine that height, which is in between negative 2 and negative 1.5. Then we would be plugging in negative 1.25 to figure out the height of this rectangle, and so on and so forth. I like midpoint. It seems like a good average of the two left and right point methods. I don't know that it's more accurate, but it seems more accurate visually, at least, because it's averaging both of them. You know, you can kind of see that for this one, all of these rectangles have heights, whereas for the right and left point methods, we ended up with some rectangles that had 0 height and therefore 0 area. So it seems like a better method, at least aesthetically. So the question is, how do you analytically do it? You know, what are the steps that ensure that you get a correct approximation each time? Now, I do want to point out that we are still talking about total area, and I'm going to underline that word. When we go to approximate the definite integral, we will be talking about net area, but for right now, I think it's easier to understand that for right now, all of these rectangles are going to have positive values, and therefore we will be finding the total area between this graph and the x-axis, not the net area. Now, total area, when we start to talk about, particle motion, total area is like total distance traveled. If you run around a track 4 times, you've ran a mile, right? Even though you end up where you started, your total distance travel would be a mile. This is what we're talking about when we're talking about total area. So we're using Riemann sums to find total area, and in this case, we are taking the absolute value of these y values and considering our rectangles as all positive. When we talk about the definite integral, however, these will take on negative values. But for conceptual reasons right now, we will be talking about total area, meaning all of these have positive area. So with that in mind, with our first x value, which is negative 1.75, the middle between negative 2 and negative 1.5, we will find the y value by plugging that into our function 1 minus x squared, but we will consider that to have a positive height. So we will take the absolute value of it and then multiply by the width of that rectangle to get 1.03125. So the area of this first rectangle using the midpoint method is a little bit more than 1, which we can kind of see because that y value is very close to negative 2. So if we were to multiply it by the width of this rectangle, which is still negative 0.5, it would be around 1, positive area of 1. So next, we're going to plug in negative 1.25 into our function. The height of that would be determined by that, and take the absolute value of that. So it would be 1 minus negative 1.25 squared. Take the absolute value of that, multiply by 1/2. Width, so width times height, and we get 0.28125. So the area of this is a little bit less than 1/3. Okay, and we're going to do that for the next x value, negative 0.75. Plug that into the function, take the absolute value of that. You won't have to in this case because it's positive anyways, but absolute value of that times the width 0.5 is going to give the area of the third rectangle, which is around 0.21875. And we're going to keep doing that for each of these midpoints, and we're going to get all of these total areas. And guess what? If we add these up, we get 4 again, which is the same exact area we got for left and right point. Again, that usually doesn't happen, but because this graph is symmetrical, it happens to occur that way this time. So the real question is, how do you conceptually find the area of all of these? Or how do you practically do it without having to do it the conceptual way every time, meaning, multiplying by these by 1/2 every time. And furthermore, you should be able to get to the point where you don't have to draw it every time. So that's what we're going to do. What is the total area? Again, I need to kind of stipulate that in the question. Not sure why I did that before. So total area means we're considering the area of each of these rectangles as positive. Again, the way to compare that is total distance traveled running around a track 4 times. You do end up at the same place, but you've traveled totally a mile, or a kilometer, depending on where you live in the world. But anyways, that's what we're going to do for now for conceptual reasons. When we go to definite integral, we will consider these rectangles as negative when they're below the x-axis and positive when they're above. So first of all, step 1 is going to be the same as left and right point method. Your interval length is still going to be 4, meaning the distance from -2 to 2 in this case. Step 2 is going to determine the number of rectangles. We're going to use the same as left and right point, which is 8. Step 3 is going to be the same. You take your interval width and you divide by how many rectangles you have, 8, which gives you the width of each rectangle, which is still going to be 1/2. Now, step 4 is going to be different. Okay, you're going to basically average all of your x values. So to determine the x value of your rectangles for your midpoint, you can write out all of these x values, -2, -1.5, -1, -0.5, 0.5, 1, 1.5, and 2. You'll just have to average each of them. To find the x value, your first x value, you would take -2, add -1.5, and divide by 2 to get -1.75. You'll keep doing that for each of these all the way up until your last x value, which is the average between 1.5 and 2. So that gives you your 8 x values for your midpoint, -1.75, -1.25, all the way down to +1.75. Definitely lots of symmetry going on here. Step 5, you're going to find the height of all of these rectangles. Again, we're finding total area right now. So we're going to assume that they're all positive by taking the absolute value of each of these y values. And rather than having to multiply each of these by the width of the rectangle each time and then adding up all the areas, again, what we can do is just add up all the heights and multiply that by the width of each rectangle, and that will give us the total area. Again, it's just like pulling out a GCF. We're pulling out this 1/2 from each of these and then multiplying it by 1/2 at the end. So for step 6, once we figure out all the height of all of these rectangles, these midpoints, which are these blue lines, once we figure out all of these heights for step 6, we can add up all those heights and we actually get 8, even though these are all decimals. And then step 7, we're going to multiply by the width of each rectangle. So we're multiplying by that GCF, which is 1/2, and again we get 4. We get the same exact number we got for left and right point. But again, a lot of that has to do with the fact that so that's it for midpoint. You can see it's a little bit more involved because you're averaging these x values. I do like it better. Like I said, it just looks a little bit more aesthetically pleasing. Now you can start to see kind of what happens when you do midpoint. You will overlap right here, and you will also underlap at times. So you will have a gap where you missed some of the area, but then you'll compensate for it by going over. And the real question you need to start asking yourself is, does it end up evening out and giving you a good approximation of the actual total area between the graph of this function and the x-axis? And as I said before, the more rectangles that you draw, the more accurate you're going to be. You're going to have less of these gaps, less of these underestimations and less of these overestimations. And the more rectangles, the more accurate your guesstimation is going to be for the total area. If you have any other questions about midpoint approximation, let me know.